Great. Hi, everyone. Welcome back to week 7 of McMahon. Good morning, good afternoon, good evening, wherever you are in the world. Today, we have the wonderful pleasure to have two speakers, and I will do a usual introduction for the beginning, both of them. Great. Yeah, so as I mentioned, we have two speakers, Dr. Wim Vos and Dr. Leonard Wee. I will introduce both of them individually afterwards. Fantastic. So just to revisit our timeline, congratulations for making it to the last week of the McMahon Summer School. The next Saturday, we'll also come back here on the Saturday to have the closing ceremony. But this week, in terms of content, today is the last seminar session, and tomorrow is the last workshop session. Tomorrow session will be given by Dr. Laya Rafi, who's also from my lab, talking about model generalizability, deep learning model generalizability, and best practices. And today we have two speakers, as I mentioned. Just before I introduce the speakers, I'd like to introduce the mentors for this week again. So if you're here, Vamsi Krishna and Ni, you guys can open your camera, and if you want to introduce yourself, you're free. Vamsi Krishna is, oh, there he is. He's a graduate student in machine learning from University of Montreal and the MILA, the famous MILA lab, the Montreal Institute of Learning Algorithms. Prior to his master's, he has an experience of 4 years working in the machine learning domain. His major areas of interest are natural language processing and speech recognition. He's been recently working on projects involving in information retrieval, document extraction, and model compression techniques for speech recognition. Besides working on his project, he likes ping pong and soccer in his free time. And Ni is our, I don't even know how many times you've been our mentor. It's been many, many times. So very happy to have you back again. I think you guys already know her, but I'll just introduce her again. She's a machine learning engineer and data scientist passionate about machine learning and deep learning in healthcare and social goods. He graduated from McGill with a diverse background in computer science, neurobiology, and mathematics. He's done a lot of data-driven solutions, competitions, and so on, and very interested in the latest advancement in the AI industry. And she's done a lot of various applications in the computer vision domains and NLP. So if you guys want to say hi, feel free. You can unmute and then just so everyone knows that we have a tutorial session this coming Friday at 1 p.m. Eastern Daylight Time. I guess you guys can say hi. Yeah, okay.
Hi, nice to be mentoring for this week.
Yeah, so as usual, introduce me like I think it's really great mentoring this week, and I hope I also get to learn like this week and give at the same time. Yeah, thanks a lot.
Thank you both very much. So great. So now I get to introduce our first speaker today, Dr. Leonard Wee. I don't know if this title that I put was is what you'll have. So, but from based on what we talked about, they talk to us about outcome prediction modeling and multi-center privacy preserving modeling approaches. Leonard is an assistant professor in clinical data science at the Maastro Clinic in the Netherlands. He's also a permanent full-time staff member at the University of Maastricht School of Oncology and Maastricht University Medical Center. He has over 10 years of experience as clinical radiation oncology medical physics specialist. and 4 years of managerial experience in the device domain. Currently, he is an academic data science specialist in responsible data science, privacy-preserving multi-center AI infrastructure, shared decision-making, multivariable prediction modeling, and multi-omics data integration. So thank you so much, Leonard, for being here with us today. I look forward to your talk. Feel free to start sharing your screen. So we'll do a Q&A session after your talk, and then when we'll go next.
Absolutely.
Awesome.
Thank you for the introduction, Eugene. I'm just going to switch myself to slide view now. Thank you for that. Yes, indeed. So that's quite a roll call of appointments I have there, but I'm very pleased to meet with you and speak to all of you online today. So just jumping quickly into it, yes, as Eugene introduced, I have 3 managers because I'm difficult to control. I work as a clinical data scientist. I'm also an assistant professor for AI for surgery. And of course, in the radiotherapy clinic, the other disclosures are, I get my funding exclusively from competitive research grants. So I acknowledge the Hannah Foundation, the Dutch Research Council, and the European Commission. And there's no conflicts of interest to declare in regards to the contents of this talk. I do have research collaborations with these 2 industrial partners, which does not have any financial benefit to me. But I do also teach hospital physicists, and for that, I am remunerated as a consultant by Electa. So jumping straight in, right? A lot of you watching this today will be deep learning and machine learning experts. You're often focused on algorithm development and getting cool solutions that classify and segment all sorts of fun things. Here's a challenge for you from a different part of science. What's this? And we have a few seconds to think about it. Some of you might recognize this, some of you might not. Well, put you out to misery. I'll tell you what it is. This is a picture of a black hole in the center of the galaxy. It's a supermassive black hole around which all the stars in the galaxy revolves around. So how do you take a picture of a black object on a black background with a very, very thin disk of material falling into it? Well, when the idea was first proposed by astronomers, they said, this is crazy. You can't do this. It's impossible. You need a telescope the size of the entire planet. To which the very clever astronomers who led this project and got this picture said, yeah, well, we do have a telescope the size of the planet. It's called the planet. The issue is you don't have one single giant telescope in one piece, but what you have is you have a lot of telescopes distributed all around the world. And if we point all the telescopes and look at the same object, we can collect the light from each of those telescopes and reconstitute the global picture of what they're looking at. And so this is what it is. Yeah. So now you know, as a data scientist, as a machine learning and AI specialist, as a clinical researcher, why we focus so much on developing a footprint of collaborations with partners all over the world. Because I don't believe we need to create one single gigantic cancer database the size of the planet. We already have a gigantic database the size of the planet. It's called the planet. The issue is, it's not in one single consolidated repository, but it's the cancer data is distributed in over hundreds of thousands of hospitals all around the world. So what we do as Clinical Data Science Maastricht, one of our big challenges is to figure out how on earth do we put that together without bringing the data into one single place. And this is why I started with that telescope image of the black hole analogy. How do we learn from this planetary data without having to bring it all together into one place? Yeah. So this is what consumes a lot of our time, a lot of my time. And this is my segue into something called federated learning, which you've probably heard about, mentioned quite a few times. If you want to power an AI model, if you want to do machine learning, if you want to do model development and model validation, at some point in time, you're going to be very hungry for data. Where's that data going to come from? Okay, so our quest for data inevitably leads us in the direction of building federated learning infrastructures. And the paradigm that we use, or the analogy again that we use, the visualization that we use, is something called the personal health train, right? And the idea of it simply goes like this. If you can't bring the data to, I'll push this out of the way. If you can't bring the data to the researcher, what we'll do is that we'll encode the research question as a software application, and then we'll send the application to the data. So why the train analogy? is because we consider the data, the patient data or the cancer data remains protected inside stations, which are typically clinics and hospitals. The data stays there and is not moved outside of the point of origin. We connect the stations with secure telecommunications infrastructure called tracks. And along those tracks, we run software applications to reach the stations, to train the models on the data locally within each of those stations, but we only exchange the models, not the data itself. And it's by exchanging the local models is how that we actually aggregate the global model, right? So this is actually no longer a new idea, right? So you know this has gained some traction and some degree of mainstreamness when the Open Data Institute picks it up and publishes a layperson's guide like this. So what is federated learning? November 21, 2022. Okay. A very good introduction to the topic. I won't have to go through it in here. This is a document that's available online, but it basically draws out a little bit more of those details in non-threatening, non-technical language about how is it that federated learning actually does what it does and gets a global model from multiple centers without having the centers actually send their data to one place. Yeah. What's really nice about that open source publication is that it actually points out some very interesting things about the impact, the reasons why there might be a benefit to do federated learning, and it's not what you think it might be. The high impact things are things like scalability and efficiency, volume, diversity of data, right? The inclusivity of data sets and demographics and people that would be very, very difficult to reach otherwise, yeah? So the avoidance of algorithmic bias and the concept of equal collaboration. And then there's the very low impact stuff, which actually turns out to be privacy and cybersecurity, right? So although sometimes when we talk about federated learning, the first thing that people ask me is, oh yes, but is it secure? Actually, when you survey the people who do this and you do the risk analysis around this question, the cybersecurity is actually very easily addressed, and it's not necessarily the thing that might lead you into doing federated learning. But it's a scalability, efficiency, volume, diversity, model robustness, generalizability. Those are the things that lead us down the road of doing federated learning. Okay. Now we knew as far as 2011, so that's quite some years ago, right? That's 12 years ago, where it was stated in Lancet Oncology, the problem for federated learning, for data sharing, is no longer really technical. And I would agree with this. With federated learning on the board for many a year now, the problem is not really technical. Rather, the problems are ethical, political, and administrative, which are difficult things to solve with technology. But here we go. The four things that people say to me, to us, when we say, can we share the data? One is, I don't know how to, right? I don't know how to make the model without being able to share the data. Okay, but we've solved that. That's no longer an issue. I don't believe that's a contention. The technical is not the problem here. Sometimes they say, well, actually, I'm not allowed to. That's actually also a fake crutch. If you want to, you will find a way to. Ethics and legality is not actually a place to hide behind. What are valid places to hide behind? I don't have the resources. I don't have the time. I don't have the people to work on this. Fair enough. We all have difficulties with budgets and resources. And sometimes what goes unsaid is simply the political. I don't want to work with you because I just don't like you. I don't want to. Well, it's up to us as researchers to grow a thick skin and say, well, that's the way life is. And often the political and the administrative is the real reason, but the reason given to you is about collaboration or working on data or federated learning is I'm not allowed to. That is false, right? The World Economic Forum. See, I told you this was going mainstream. The World Economic Forum picks this up and talks about how, in an 8-step guide, to put together a consortium to do federated learning. Right? And this is also available as a public open access document. So we're in a session with a lot of people who are interested in AI and machine learning. And this is a funny thing for me to say, right? The key enablers for this technology is not the maths. It's not the code. It's not the technology, right? It's the legality, it's the politics and the administration, right? So what we have done is in a number of our projects, we have generated templates for how a consortium should be put together and what elements that consortium should deal with and define. We have an infrastructure user agreement as a template. We have a data management plan for how to put these data stations together. We have already independent assessments of the data protection and the data security impacts to satisfy very strict European laws. And of course, we have the technical blueprints. And all of these templates, thanks to the Argos Consortium and the Strong IA project, which I'll mention a bit later on, all of these templates, if you write to me, we'll give it to you, right? These are all public open access documents. Fill in your name, fill in your project, fill in your partners, away you go. And I'll mention to you later why I think this set of documents that we have is actually a really good starting place so that you can start working on the technical stuff and not get bogged down in the legal and the administration. All right. Our project, Argos, is the one and only federated deep learning study registered on clinicaltrials.gov. Use that NCT code there and you'll be able to find out all about it. All right. The data, sorry, not the data, the source code for the stations and setting up the tracks, well, that's open source too. Of course, it's on GitHub. You go to it, you will find it publicly open, accessible. It's still work in progress. It's not fully up to date every time, but I am working very hard to keep it up to date as much as possible. But all the code and all the legal technology is now open access. Our evolution of federated learning looks a little bit something like this, right? Many, many years ago, as far back as 2017. This was tried with 4 centers in the close vicinity of Maastricht. There's Maastricht where I work there in the Netherlands, right? So already this was a very early proof of concept, was that we could fit 5 different local models at 5 different hospitals, but we could join the models together to get a global model that describes all the data. And we could do this global modeling, global prediction outcomes modeling, without transferring any data outside any of those 5 hospitals, right? And that took on another incarnation with not just clinical data and learning a clinical prediction model. Well, you can do this with image-based features as well. And I will leave it entirely up to Wim, the second speaker, who will tell you all about radiomics and all the amazing things it can do, right? But this is just a point for me to say, it doesn't actually matter what kind of data you want to do federated learning on, right? As long as the data is structured, you can figure out a way to do this, right? And here's 2 years overall survival again. It's one of the old problems that we always try to predict and prognose in our predictive models. This was done by Timo and Frank a few years ago, and this won an Astro Award when they published it in 2020. This was 7 centers around the world that managed to find 40,000. So I'll say that again, nearly 40,000 lung cancer patients, of which 20,000+ was actually used for the prediction modeling of overall survival in a fully federated way. So no physical data sharing, right, across these 7 hospitals. So you can see that it scales in terms of the numbers of patients, but it also scales in terms of the number of partners you can have in your consortium. We started a rare cancer project, anal cancer, with only 3 institutions, Leeds, Maastricht, and Oslo. We published this already some years ago. The last incarnation of AtomCat, AtomCat 2, was completed earlier this year, and it was up to 16 partners, right? So what I want to show you here is that when we started a prototype with 3 partners, it was actually not that difficult, barring a couple of software updates and testing of the technical infrastructure, to go from 3 to 16. Yeah, so there's scalability in terms of your sample size, but there's also scalability that you can think about in terms of the number of partners and the number of footprints and the number of geographic locations you can work with around the world. All right. Finally, this is Argos. Argos stands for AI, for gross tumor volume segmentation. The example that I'm showing you here is, of course, a lung tumor segmentation. And what we want to get is we want to get an deep learning algorithm to produce the picture on the right-hand side that you can see on your screen, which is very close to, but maybe not exactly always perfect with, what a clinician delineates, which is the thing that you see in the middle of the screen. Now, the AI, the deep learning algorithm that we're using in Argos, is really very boring. It's a very standard 3-dimensional UNet. It's nothing really that special, right? But for me, what's the interesting things to talk about it? You all know about UNets. I will not pretend to tell you about UNets, but, all right, what we did here with Argos is we fully opened the source code for doing the federated learning, and we'll also fully open source the models itself in due time, right? We got 22 institutional partners across 10 different countries, all to sign the same piece of paper to say that federated learning was going to happen, all right? Including very difficult legal jurisdictions to work with, including the EU and Switzerland and US and China and India. And we did this in 2021, which predates by 2 years the framework signed 2 weeks ago, which is bilateral data security arrangement between the EU and the US, which works for companies like Meta and Facebook, but addresses nothing for clinical research data. Well, we were already doing federated learning between ourselves and partners in the US 2 years ago, right? So this for us is a non-event because, right, federated learning already was compliant with the basic core legislation of these countries. It did not need any special tweaks on top of that, right? Inclusivity and diversity, I will show you the partners perhaps in the next slide. We wanted to include small clinics and low and middle income countries, right? We did not want to insist on everybody having the latest, greatest GPUs, and we were not in a position to hand out, you know, dozens of very expensive GPUs to people. That's not how we work, right? So it was bring your own GPU, basically, whatever you have in your lab. And we did this, interestingly, with no funding. So everyone who worked on this, their time and their computing resources was whatever we could dredge up in the clinic. We were not specially funded for this. People joined this project because they saw the value in it. They saw the value in what they would learn from participating in something like this. But we didn't give out a single euro or a single dollar for people to participate in this. They did it all out of their own pocket, out of their own resources. Huh? So I think this is something to keep in mind, compare with other big name, very famous, very expensive and company funded projects that you will hear about in this domain. So what Argos was, again, this picture will be very familiar to you now. It was deep learning without sharing patients' images, right? So the details of the infrastructure is not that difficult to work out. I leave the diagram there for you to look at your own leisure. But on the left-hand side, I give you the list of the clinics that we were participating with. And you can see that they do cover quite a good chunk of different parts of the world, including UPenn and the Moffitt Cancer Center in the US. Okay, in terms of sample size we could get, ignore the mean dice. We basically sent out an untrained algorithm for 0 iterations. The only thing we wanted the algorithm to return for us was the sample size that we could see in the consortium. And those are the sample sizes there printed at the bottom of the violin plots. Add up the numbers if you wish, they would come up to close to 2,500. All right, so that's a sample size that we can pull together in a short time using this kind of consortium federated learning approach. And the early results we were getting, training and validation curves, look a little bit like this, right? What we see is that we see all of the centers, the global model converges on all of these 12 centers very, very quickly. What we see is that, yes, there is a little bit of noise. We see heterogeneity between the centers, but by and large, what we see as well is all of the centers learning together. There's no strong evidence to suggest that one center is being overfitted at the expense of the others, et cetera, et cetera. There's certain heterogeneities that we cannot resolve, right? But for the large part, we see all 12 of these clinics learning a global model and gradually converging together. So this is really promising. And we will, of course, make these results, we'll publish all these results. And as I mentioned earlier, we'll make the models open access and available to people as well, right? And to finish up with, because I really only have a short time and then I want to invite questions, one of the things that Yujing and others have asked me to ponder upon is this idea of implementation, right? Is to go beyond this idea of, yeah, I can train a model. Now you can train a model on your own data set, or you can train a model like I do in distributed data sets all around the world. The really key thing is to ask, well, what's next, right? Now, one of the things I stumbled across, I just wanted to show you this anecdotally here, is especially when you do segmentation or classification type machine learning and deep learning jobs, we sometimes bump into this thing where the clinician might actually say, well, you know, it doesn't look acceptable or it doesn't look quite right to me. So we did a Turing test. We actually did a triple-blinded test, right? This is a different study on body composition segmentation, so not lung tumor. But we asked if our clinicians could actually see the difference between a human segmented result and a machine learning, a deep learning segmented result. And I think, yes, they sort of can, right? If you look at the bar chart on the left, the clinicians, the human clinicians have a slight preference to rate the human operator as more likely to be acceptable. and they have a stronger propensity to rate the deep learning as being unacceptable. So what this means is any halfway useful clinician can probably just look at whatever the results of your AI is doing, and they can probably figure out reasonably quickly whether a human did it or an AI did it, right? But what does it really correlate to? This sort of quantitative gut feeling thing of clinician acceptability, yeah? But if you look at the dice scores, that's roughly what it correlates to, right? There is this very gradual slope from left-hand side to right-hand side when you look at the box and whisker plots. That seems to be, okay, maybe what they're looking at is they're looking at this gradually worsening trend in the dice scores. But then again, the clinicians will probably be the first to advise you that the dice score is not the be-all and end-all of everything, right? So here's a quandary for us, right? Visually, they can see a difference in something. There is a difference in style. There is a difference in preferences. It somewhat correlates with the geometric dice score. But then if you ask them, does it actually have any quantitative meaning? When you calculate the muscle to fat body composition indices, the answer is absolutely not, right? All of these measurements compared to a human are within 1%, 1.1%. So I'd like to challenge the clinicians as well to come up with a blood test or a pathology test result where they think the margin of error is 1%. It's usually more than that, huh? But what we're finding here is that what the humans are rating is really more about their preferences, about what they want to see, right? But when you calculate the quantitative metrics from the segmentation or from the result of the deep learning, there really is no tangible difference at all, regardless of whether the clinician has qualitatively deemed it acceptable or not, right? So what's next? On this, I divide my slide into two. In green, I'm giving you some opinion there about what I think we, or I, and my team to date, what we do well. And in red, what I think we don't do that well yet and what we need to do a lot better on, okay? None of this, machine learning, AI, deep learning, none of this works until you prepare the data into a fit state, right? From which you can actually do centralized or federated learning. That goes without saying, right? So we do have the tools, and we've invested a lot of effort into making tools available, giving it out to our Argos partners and others so that federated learning can happen. The other things about scalability and diversity and generalizability I've mentioned to you before in the early part of this talk. Now, I wanted to just remind you again that this Argos infrastructure was prototyped on segmenting the lung gross tumor volume, but actually, if you think very carefully about it, the deep learning task is agnostic to the clinical problem. If you change the data and change the model, you could learn anything you want on the infrastructure, right? Today, we're doing GTV segmentation. Tomorrow, we could be doing substructures of the heart. The day after, we could be doing classification of radiological extranodal extension. The day after that, we could be doing deep survival models. You take your pick, right? The architecture is agnostic. You change the model, you change the data, you learn, and you address a different question through federated learning. That's why it's scalable, right? Some of the things that we don't do well, and this really hurts a lot when we think about the implementation of what we learn when we do centralized training or federated training, right? It's really two things: having an impactful clinical question, and we need our clinicians for this, and the clinical data has to already exist. I've had too many discussions with clinicians that have amazing clinical questions, but as soon as I ask them, okay, have you been recording this for the past 5 or 6 years, and can we mine it to answer your question? No. Boom. Okay, let's go back to square one. Let's figure out how to collect the data first, right? Then the other thing that comes up is not to be, as I've mentioned before, not to be overly obsessed by the geometric aesthetics or stylistic preferences. Clinicians are really, really smart. They can look at the result of an AI and reasonably quickly figure out whether it's more likely to be machine generated or more likely to be human generated, even with a very good AI model, right? To a degree. They'll learn the differences very, very quickly. So the question there is not to be overly obsessed by geometric aesthetics or stylistic preferences of clinicians about what is acceptable or what is not, or what looks good or what doesn't look good, but really evaluate the AI model on what effect does this has on the patient treatment pathway, on the decision-making that the doctors do. And to that end, I think effectiveness is much more important than efficiency. It doesn't matter so much that your model can cut down the task time from 3 minutes to 3 seconds, right? The real question is, what happens to the patient at the end? Does it flow through the system and actually deliver something tangible, right? A tangible improvement in patient care rather than just saving a few seconds, right? Shaving a few seconds off the workflow. Effectiveness is about the entire clinical procedure and not just an AI tool bit that might make 0.1% of the entire workflow, all right? And the models that we work on, the machine learning and the AI models, they probably widen the space for clinical decision-making, right? They probably widen the space and bring into question the possibility of alternative treatments and preference-sensitive treatment decisions between the patient and the doctor, which raises for me the question, in all of our work, in all of the math hacks, in all of our discussions about AI and machine learning and deep learning, where's the patient in all of this? Ever talked about this with a patient? Ever asked a patient with cancer what they want? Well, we do, right? We at least we start to, and we know we have a long way more to improve. So to finish up my manifesto for something called a triple intelligence paradigm and a small advertising, right? I think the way of the future is not that the doctor and the patient make decisions, right? No, not the doctor solely making the decisions, not the patient watching an ad on TV and telling the doctor what medication they want, but there is a cooperation there. But the doctor has a special kind of clinical intelligence based on their schooling and their expertise. The patient has a different kind of special intelligence based on their knowledge of themselves and their lifestyle and what they want to get out of having treatment, right? And well, the field that we are working in, the machine intelligence, the data-driven intelligence, well, that's a different kind of intelligence and perspective too. And the manifesto here is to think about a triple intelligence paradigm, right? It's no longer the pilot and the co-pilot, the doctor and the patient flying the plane, but the pilot, the co-pilot, and the flight engineer, right? The doctor, the patient, and the machine algorithm assisting in a collaborative framework, and we can discuss what that framework ought to be to make better decisions and to make more effective patient care, not just more efficient and shaving a couple of seconds off something that's meaningless in the whole workflow. All right. So things we're working on. We need to get better with design and capture and reuse of data in ecosystems. We have to do this with doctors and patients in a co-design and a co-creation paradigm. Open source, open code, open science continues to be ours or one of mine always manifesto, right? I think it lends itself to a great deal of scalability and transparency, right? And of course, we are more than happy to share the legal and the ethical and the governance technology that we've been developing in Argos. And also, this is my ad, this is a plug for Strong Aya, the European Commission funded project, where we are doing these things, ecosystems of data capture, data reuse, co-creation of use cases with clinicians and patients together, right? So we're a long way away from finishing that story. I hope to come and tell you a lot more about it in another time, but that's good. I think we have some things that we're good at and a whole bunch of things we need to get a lot better at. So on that note, I don't know, I haven't been keeping a full eye on the time, so I do apologize, Eugene, if I've gone over, but I just wanted to say
you
to
were
everyone,
perfectly on time. Thank you so much for the talk.
Thank you. And if you wish to connect and discuss more with me, please scan that QR code. It will give you my details. Thank you, everyone.
Yeah, thank you so much. We have about 10 minutes for some Q&As. I have a lot myself. I was talking with my colleague Jose. He also is very much in love with the presentation himself as well. So I assume we'll have a lot of questions, and we'll start firing them away now.
Please do. I'll do my best. I may not know all the answers.
Right. Arhen asked a question, how would you define deep survival models in the context of tumor models? I think I've heard about like specifically a package called DeepServe, or if that's what you say.
Yeah. So there's a few different ways to look at this, right? So I believe DeepServe on its own will simply require an input of some number of engineered features, or some number of features. Let's just call it that. And the DeepServe model or the DeepServe paradigm just breaks your survival time interval into consecutive bins and basically makes some kind of a chained outcome prediction over the time period. So I myself, I'm not an expert on the mathematics of that myself. But the other way to think about a DeepServe model is, and maybe Wim will talk a lot more about this, is you could use an image as an input, right? You could use an image as an input where the image is firstly going through a large number of convolution and compression layers, right? So what you then basically have is you have a compression of the layers down to some kind of a finite feature space, and then you use that finite feature space in a deep survival prediction with the known outcome labels, supervised learning, to fit a survival model, right? So so I think it's an interesting one. I think our clinicians have a small preference of seeing the survival probability change as a function of time, rather than me just telling them yes, no, the patient being alive at 2 years, right? So again, this is something to discuss with your clinicians. What's the most clinically impactful way to think about and interpret the problem? But certainly all of the tools are there. There's nothing magical about taking a ResNet or a VGG, for example, boiling an image input down into a number of features, and then using those features in a deep survival model to try to predict, let's say, the survival outcome or the local regional recurrence or something of that ilk, some sort of time-dependent outcome, yeah, rather than just a fixed binary yes, no at a constant time point. I hope that's useful.
Perfect. We have another question regarding the diagram, the three-way diagram they showed at the end with the patient, machine, and doctor. Reza asked, where's the medical physicist location in that?
Yeah, good question. Where does a medical physicist want to be? Well, I think I have a very biased view about that, right? I have had discussions with medical physicists before, some of whom say they want to be nowhere in the diagram, right? Because this is about data, this is about clinical research, this is about magic things that doctors and patients do with each other that have nothing to do with physics. I disagree respectfully with that point of view, but I also respect the fact that some physicists say that computations and data and machine learning and AI is not their cup of tea, and they don't want to be a part of it. That's fine. Other physicists do. Other physicists see that there's a lot of a role for how you might incorporate some degree of machine intelligence, doctor's expertise, and patient-dependent preferences into, for example, automated treatment planning, right? Now, those physicists I have a lot of time for to discuss, because there's a lot of opportunity to ask really interesting questions. Very few answers that we know at the moment, but that's fine. We can ask lots of really interesting, impactful questions. So where the medical physicist is, I think I'm gonna do a really weaselly thing and bounce it back to you. Where do you want to be, right? I see two kinds of physicists and probably a whole spectrum in between. Some don't want to do anything about it. Others are really interested about learning from the data, from the treatment plans, from the medical imaging, trying to help the doctor and the patient, choose the best kind of treatment, and they really want to be involved in this field. The reason for my bias, I am a medical physicist. I've been trained as a medical physicist and worked in the clinic for 12 years, and as I was a head of department of medical physics, and I transitioned into this role in clinical data science. So where's the medical physicist here? Well, I'm a sample size of one about where you could be, right? But I think the question is open. Where do you want to be as a medical physicist? And maybe that's a question back to you.
So do you do more of your time on the data science end, or do you still do clinical physicist work now?
Me personally?
Yeah, I'm asking you.
Yeah, I'm in full-time research now, right?
Okay.
So I'm no longer treating patients. I miss that very much. But at some point in time, you've got to stop doing two things badly and start doing one thing really, really badly, which is what I'm doing.
Great. We have another question from Hanif. How would one address challenging data such as highly metastatic patients with over 20 lesions, where input data grooming might not be feasible to segment by human? So rare disease. Yes.
Yeah. So there's a combination of questions there, right? So one is in this topic of federated learning, I think I mentioned a slide on it. One really strong use case, right, is something like this, right, that I'm showing you on my screen here. If it's a rare disease, it's very difficult for one clinic to have enough examples to do the work and train a model or train a segmentation all by itself, right? Rare diseases I really like because it forces you to cooperate with your neighbors. You have no choice but to collaborate, right? Nobody sees enough of one thing to be able to do it themselves. So metastatic diseases are multi-metastatic conditions, the ones that are really difficult to, perhaps they're rare, but perhaps also they're really difficult. Those are the kinds of conditions I think that would be great to try to collaborate on, especially in this domain of federated learning. And it's one of the things, anal cancer, head and neck cancer, those are the sorts of diseases I work on a lot. There's a different dimension to that question, is that it's complicated, right? So the data quality might be very low. Well, the data quantity might be low, and the data quality might also be very low. You know, you've got to treat this patient really, really quickly, and you don't have time, right, to sit there for a day delineating the outline of every metastasis beautifully. You're just going to have to go, yeah, whoop, bang, zap, treat the patient, right? So how do we deal with data quality? How do we deal with biases in the data quality that says that patients with bad prognosis or multi-metastatic end-of-life diseases, their data quality is just really poor compared to the patients that we do try to cure? That's a bias, right? That is a source of bias that we do have to watch out for. Now, that's a really difficult one, right? That's a really difficult one because it cuts right back down to what's our core priority? What data do we generate? What data do we use in the routine treatment of the patient? And then how do we maximize that data that we've already got to do something like machine learning or prognostic modeling from it?
Yes. Hossein, do you have questions? I know you're very excited.
Yeah, sure. Thank you so much. That was amazing. It was a really inspiring talk. I'm just wondering, so, we have like a specific model architecture. We've decided to go with this architecture, and now everyone trains on this one architecture, and they share the weights, and they do it in a federated way. What if a new architecture comes along? Now everyone has to like retrain with the new architecture, or is there like a shorter way to kind of like move from one architecture to the other architectures? Because
Hussein, what would you do if all that data was in one disk under your computer desk and you had a new architecture? What would you do?
Well, I mean, first of all, the resources to train for that, like all that data, is also another problem that like no one has. Like, I mean, they have to share like the GPU resources, obviously. But I don't know. I mean, transfer learning.
But Hussein, I guess it's a cheeky question too, right? Because the way I understood your question was, you had some data. Let's ignore the fact whether it's in your desk or in 20 places around the world. You have some data. You have a deep learning architecture. You trained it, right? And now you have a new architecture. Oh, it's a double UNet. Woohoo! Hey, excellent. Oh, it's a 3D UNet. Well, how would you reuse, Hussein? How would you reuse your existing model?
I mean, definitely transfer learning has to be like a part of it too. So that we
and so that would be my same question. So federated learning and centralized learning is no different whatsoever in that sense, right? I have a pre-trained model. Whether it's trained on one data set or 20 data sets, it doesn't matter. I have a pre-trained model. A new architecture comes along. Unless I figure out a very clever way to transfer the weights from the old architecture to the new architecture, and I think that is very much not trivial, right? What I can do is I can ring up my partners in Argos and say, hey guys, turn on your machines, turn on your 20 machines, because I have a new model that's going to come around and relearn it. Okay, so that's possible. So data reuse, data recycling, reuse of the same infrastructure to train a new model is always possible, right? But physically copying the weights from one architecture from some number of hidden layers into another, I'm not sure you would even do that, even if all the data was sitting in your desk. So
that's a fair point. Yeah, thanks. Thank you.
Yeah, thank you so much, Leonard. Especially with the previous points on the hurdles for the legalization between the different departments and trying to get the data together. How long did it take for you guys to get that together? Wim has a question after.
Sure. the honest answer, Eugene, the world record, I think the world record, or at least my world record, was in the Argos project. 7 months.
Oh,
From
wow.
from the first signature to the last. So this is a lesson I think machine learning and deep learning and technical people sometimes resolutely refuse to learn, right? Is that what we do as machine learning and deep learning and algorithmic people, we are the tip of the iceberg. But there has never been a project or a ship that has been sunk by the tip of the iceberg. The legal, the admin, and the politics is all the rest of the iceberg under the surface. And you know that that's what sinks ships, right? So when we do a project like this, when I run a project, when I'm a PI of something like Argos, right, I never let myself get blinded by the fact that I'm just going to develop some code and shoot it out and it's going to be amazing. Well, it's not, right? There's going to be a lot of making sure that all the paperwork gets done, all the laws in all of the countries get obeyed, data security is fully satisfied by everyone. And then I can get on with the fun bit, which is like building and training the models. Yeah.
Right.
So.
Yeah. No, absolutely. That's incredibly impressive. Wim has a question to raise his hand.
Yeah, maybe more a remark or in addition to what Leonard said, because he has addressed a lot of the legal aspects, all linked to the shareability of data. But I think for me, the biggest difficulty in distributed or federated learning is the legal aspect from the other side. You know, if as a company you want to train a model and you have a specific architecture or you have knowledge in the parameters that you use to train your knowledge, that is IP, and it's very hard to obfuscate that part in a federated network. And what I see from a corporate level, even when federated networks live and are usable, training a specific model on that you want to commercialize afterwards has a massive amount of risk, because it is almost 100% transparent to all the centers you send it through. And this is something which is not solved at the moment. And I think if we want to take it to the next level, it's something that will at some point need quite a bit of attention.
So for everyone else in the call, I think I agree with Wim's point of view too, to a degree, right? Because Wim is speaking as a CEO of a commercial company, so he has this valuable perspective to give, and his perspective is valid, right? So if you have a look at the diagram that I'm sharing on my, I think I'm sharing on my screen here, yeah, is that we in a research consortium with no commercial partners, we still try to obscure the model weights as much as possible, right? What you see on this diagram here is I, the researcher, I send out a model to train. Now, if you have a look at the cartoon on the top right-hand side, your top right, during training, each data station is training the model on its own data, but it is not sending the partial weights to me, the researcher. It's sending its partial weights to a disconnected party that doesn't share them with me for aggregation. And only at the end of the iteration or the epoch or the cycle will the architecture tell me, the researcher, that it has received weights from X number of partners, it has averaged them together into one single model, and I only get access to that single model, okay? That single global model. What this means is, if you look at this diagram, no partner is allowed to talk directly to any other partner to share weights or to ask for data. No, the partial weights only get shared to one central location where even the researcher is disconnected from it. And the researcher only has access not to local institutional weights, but to the global weights of all the institutions averaged together, right? Wim's point is another to say that once I have the global model, right, now this becomes a good discussion, right? Because then we can argue from that final global model, is it possible to re-engineer the existing data, right? And
Leonard, I think that's not the point I want to make. It's not about it's not about the weights. It's about the factors that you use to calculate the weights. You know, it's if you take a simple linear model, it's not about the weights of your linear model. It's about the factors that you put in, and that is something which is extremely hard to make obscure for the users. And you know,
but Wim, the counterpoint there, I think this is a really good discussion too, because it brings out a lot of interesting things, right? If I learn a linear regression model and I print the coefficients, sorry, a logistic regression model, and I print the logistic regression in a paper in medical physics, you can see the coefficients, right? So is
Yes.
that not also compromised? So maybe what we're actually needing to find is a common language about who owns the IP, right? Whether the model is reversible or not, whether the weights should or should not be revealed, whatever that is, maybe the true question we are trying to figure out is how do we deal with the IP, right? And how do we share the IP since so many people contributed to the training? If one of these beneficiaries is a commercial company, how does that get shared in a fair and equitable way, which is an excellent question. Right?
Yeah, thank you. That was a wonderful discussion that we had. Thank you so much again, Leonard, for the great talk. I'm gonna have to email you later on for more questions myself.
Oh, please, yeah.
Yeah,
That's
thank you so
true
much.
for everyone else too. Please feel free to email me, and thank you for your attention today.
No problem. So right now I'm just going to quickly also introduce our second speaker, Wim. Let me share my screen again. There we go. Fantastic. Great. Our second speaker is Dr. Wim Vos, as Leonard also mentioned before. He is the CEO at the company Radiomics for insight-based decision-making. He's the driver behind Radiomics Vision, which is based on his knowledge gained in over 15 years in different leadership roles in quantitative imaging companies. Using his experience and network, Wim's strength lie in in identifying unseen opportunities and leads the team using out-of-the-box thinking. He represents a resource for Radiomics, which, thanks to his business spirit, has shaped its pathway towards success. So before he joined Radiomics in 2019, Wim was also the co-founder of Fluida, where he initially led the technical development team and was afterwards responsible for the global commercial activities. He also holds a master's in aerospace engineering and PhD in physics from University of Antwerp. Thank you so much, Wim. Please go ahead and start sharing your screen.
Well, thanks to you foremost for the invitation. Trying to share my screen now. I hope you can see it. Right? Okay, good. So I'm gonna take a totally different angle than the angle from Leonard, stepping away a little bit from the research side in image analysis and really going to how it can be used to gain actionable insights and how to use them in the daily practice. And I think Leonard's last slide that contained the red things where the research state is, I think we really focus on that side. How can we bring this to patients? How can we be relevant? And I want to use the next 30 minutes to guide you through the process that we're using at Radiomics. So on myself, I think Zhu Jing gave a good introduction. I'm an aerospace engineer that went into image analysis back in 2005 and have been working on respiratory diseases for 13 years and now for 4 years on oncologic diseases. The company that I represent is Radiomics. We're based in Belgium as a headquarters, but we also have a subsidiary in Montreal. We are close to 40 people, a lot of PhDs and medical doctors in the team, very, very different nationalities. We mainly work with big pharma and small biotech companies in the development of their new therapies. But we also have been very active on the granting side with 9 to 10 funded collaborations in Europe and Canada. A lot of funding that went into these projects and a lot of funding that went into the company to contribute in these global research efforts. Now, let me start on advanced image analysis. And for me, advanced image analysis should definitely not just be a descriptive or a measurement tool. We all know that scans can be quantified quite easily by machine learning purposes. And here's just a multitude of things that could be extracted from a CT scan from a lung, going from lung or lobar volumes, airway analysis, hyperinflation, emphysema, blood vessels, airway wall dimensions, all these kind of things. And very often when we look at how these things are described, we see that people are just measuring, giving this lung lobe is this big and that lung lobe is that big. And I think this is not where we should stop. We should go further than that. The moment we bring it back to the patient, we say, well, we see that, for example, the right upper lobe in this patient is 1.5 liters, but it's actually twice the size that it should be. At that moment, we start making sense for the patient, because we know there's definitely something very wrong at that location for the patient. And with my background, I've also been working, for example, on predicting where inhaled delivery of medication will go, which is also quite relevant if you want to treat a patient with a certain inhaled drug, that you can estimate how much of that drug will go to the regions where it needs to do its job. Now, if we look at medicine in general, I think there is some main challenges, and the main challenge in clinical practice linked to screening, to diagnosis, to the follow-up of treatment, or the selection of treatment and the stop or the change in treatment. And this is not so dissimilar in the development of new therapies, where we're looking at the safety or the efficacy of a certain drug, trying to find the right dose, the right target population, look at the efficiency of that treatment in a general population. And on the left-hand side, what we're trying to do is link the individual patient to the right treatment. And on the right-hand side, we're trying to find the right patient population for a given treatment. So when we look at predictive modeling in this setting, what we do on a patient level in the clinical practice, we're also doing similar things on a drug level in the development of new therapies. Now, if we look at solid tumor care, there we can ask ourselves the question, are we failing or are we cheating our patients? And I think very often we are failing our patients. If you look at new targeted therapies, a lot of them fail in their development trajectory. And when we look at the efficacy they have in patients, there is only a very small fraction of patients that really have a durable response to a targeted therapy. At the same time, we see that the cost of those therapies is massively high. So this might be us cheating them. And it's not only the therapy that is crazily expensive, it's also the whole diagnostic battery that goes with it. And if we see costs, for therapy and diagnosis combined that are multiples of a monthly income of a patient, we might ourselves asking the question, well, are we doing the right thing? Especially if we see in a lot of targeted therapies that the main outcome represents maybe a survival benefit of a couple of months, which is very minor. Or have we been missing out on something? And we at Radiomics believe that there's one element in solid tumor patients that really has been ignored for a long time, is the fact that many tumors are biologically diverse. I think Hanif asked the question before, what in a patient with a lot of metastases? Well, here you see a patient with 88 metastases in the lung. It's a primary uveal melanoma patient with 88 metastases in the lung, and there were many more in the rest of the body. And if you look at how a therapy works in such a patient, you see that there's always a good fraction of lesions that do respond to the therapy, but there's also a good fraction of the lesions that does not respond to the therapy. And I think this is a reality for a lot of the late stage patients. And those are the difficult cases. And those are the cases we should also not forget to have a look at. And at Radiomics, we are really convinced that if we can come up with a way that we could characterize those lesions almost individually, one by one, to understand what their genetic or biological buildup is, we can come up with a combination of therapies that we can give together to the patients in order to not just extend their life a bit or improve their quality of life, but really also cure those difficult patients. Now, on the radiomics technology, I think most of you are aware that on an image, you can do segmentations. You can quantify the regions of interest that you have segmented, and you can do some predictive modeling to link it either to therapeutic outcome or biology. But it is important to do it in the right way and to find the right use cases for each of those parts of the technology. And within our company, we're working a lot on segmentation models that can work on the segmentation of an organ or a tumor or some kind of radiological pattern, or some models that can help with synthetic contrast creation in order to more easily find, for example, blood vessels in certain patients or other things. We work on quantification in a very traditional way, the voxel-based radiomics that most of the people are using, but we also do a lot on mesh-based radiomics, where we convert the segmented models into mesh 3D models, which have the advantage that they have sub-voxel accuracy. You can look at shape in a totally different way. You can also look at some kind of semantic features, for example, the connectivity with the surrounding blood vessels. And all of that need to be considered in a very strong way. Is what we see robust? Are those quantifications real, or is it just noise that we're measuring? So we put a lot of effort into phantom work, whether they're physical phantoms or digital phantoms, making sure that all the aspects of the image analysis are investigated. Are the formulas we use correct? Do they comply with standard? Is it reproducible? Is it stable? Is it repeatable? Is it generalizable? If we generate a mesh, is that mesh of good quality? Is it the right quality of a mesh that we use for the evaluations that we want to do? And all that to allow for intuitiveness and explainability. I think it's very important when we want to bring predictive models into the clinic that the clinicians really understand why a model is making a certain decision. It can be through activation maps when you work with deep learning, that you use that to really drive the insight of the clinician, where it's this zone that is contributing to the decision. But it's also when you use other more handcrafted radiomic features that you make certain that the clinician can understand what that feature is really giving as information. And then you can put all of that together and start using it. The first and most simple use case is probably to quantify the response to therapy. So here you see the liver for an HCC patient under therapy, and you can see the lesions at baseline, and then you see the coloring, which is actually indicating the volume change. So anything which is yellow-green describes a shrinkage. Everything which is orange-red describes a growth. Everything which is gray is quite stable. So you can follow up this patient over time and really for each of the individual lesions, start quantifying what happens under a certain therapy. You can use that under multiple dose levels. And for example, here it's in a population of patients where we saw that from dose level 3, we started seeing some lesions disappear, which we didn't see so much with the previous dose levels. Dose level 1 didn't even have shrinking lesions. So this can help you in a drug development trajectory, gain understanding of where is my dose starting to have an effect on a patient, and what's the most optimal dose to take forward in a drug development trajectory. We don't have to stop with size alone. So you can go further, even in situations where, for example, RECIST as a major axis length is not showing anything. There might be other radiomics characteristics which are already showing a difference. This was a very small population, I think 10 or 11 patients, where we could see that there was a textural tendency to go to more uniform lesions under therapy. There was also less spikiness observed, which means that the tumor was less protruding in the surrounding tissue under therapy, which did not result directly yet in a change in size, but there were other characteristics that showed that the drug was active already in those patients. Now, you can also look at diagnostic capabilities, and this is an example that we've done in head and neck cancer patients, where we've built a diagnostic tool from the imaging that predicts the HPV status with an AUC of 0.76, and actually showing that as compared to the P16 staining, the classification of groups in positive and negative had similar survival characteristics, even up to a very long point in time. The time here is 60 months, for example, so it's already close to 5 years that we're looking into time where both methods actually have the same diagnostic and prognostic capabilities. The big advantage of using an image to look at underlying biology as compared to tissue biopsy and liquid biopsy is that you're non-invasive, but the main advantage is that you can look at all visible lesions. With tissue biopsy, you look at one lesion. At liquid biopsy, you look at all of them, but you average them out, or you look at a central read of all of those, so you don't know how the heterogeneous spread is in between those lesions. So that's definitely an advantage of looking at that through an image. We can also go completely prognostic. This is an interesting one. This is a set of non-small cell lung cancer patients that were treated with chemotherapy, where we looked at RECIST as a measure of response. So this is a RECIST classification during the trial. And you can see that the RECIST responders definitely have a better survival benefit than the RECIST non-responders. There was 15% of the patients that were having a RECIST response in this trial. And what we actually try to do is, based on the baseline data, predict which patients would respond. And actually what we saw is that we could build a predictive model where the orange line are the patients that had a prediction to survive quite well under chemotherapy. And you see that the survival curve is quite similar to the ones that have an observed response with true RECIST. But we're not looking at 15% of the population, we're looking at half of the population. And then we're able to distinguish the other half, which really don't have a benefit of this therapy and are dying off much sooner than the average survival in this population. Some considerations about data, and I think this is linking back to Leonard's presentation before. So Leonard mentioned that having access to huge data sets is important in order to capture all the kind of variabilities that exist. From our point of view, and from my point of view, I also want to mention that this can be dangerous because you have data sets which contain huge differences or huge different levels of noise. And there's always a risk that the model might be capturing that noise somehow. In the approaches that we take, working with pharma and biotech, we're on the other side where we have high quality curated data sets, where when you develop a model, you gain deep understanding of what are the parameters that are of interest. And then you could afterwards take that model and bring it into a real life setting in order to see if the parameters that you capture to be relevant still can be measured in that data set. So it's a slightly different approach in one where you use a big data set in order to cope with all the variabilities that can exist, while in a small data set approach, you'd really try to capture the elements that matter in the predictive model, and then you test if you can still measure those elements in a more broad and variable setting. Now, we have shown that such an approach, where you go with small cohort, high quality input, that you're able to develop models that are often outperforming the ones that have come from a larger cohort that have poorer data in them. And maybe where we're working towards and what we believe is the future usage of this kind of advanced image analysis in the clinic, we are very much convinced that at one point a patient might come into the clinic. This is an example of an HCC liver cancer, where an image analysis could be used to look at the prediction of the biological state of these patients. And here, for example, you see 2 lesions in the liver, and both of them seem to be PD-L1 positive, which can, at that moment, allow a clinician to select a treatment that works on PD-L1 positive liver cancers, in this case, nivolumab. We could do a prediction of the response likelihood to the selected drug. And if the likelihood of response is high enough, the clinician can start the treatment. And after a first cycle, the patient can come back and we can look at what effectively happened to those tumors. So in gray, you see the overlay of the original tumor. So here you could see that the tumor on the bottom is definitely shrinking quite well. The tumor at the top seems to go grow a bit bigger, but becomes more spherical, less protruding into the surrounding tissue. So it could be a case of pseudoprogression. Based on this data, the clinician could do a second prediction of the response likelihood of the selected therapy. And seeing that, well, here in the case of the bottom tumor, it got a bit better. The top tumor, the response likelihood got a bit worse. But the clinician might say, let's give it another cycle. After 16 weeks, the patient come back. Now we see a clear progression in the top tumor. We see even more response in the bottom tumor. At that point in time, the clinician could say, well, let's do a restaging of the biological state of this patient, which shows that the top tumor now became PD-L1 resistant. Luckily, there is another pathway active, so the clinician can prescribe a second therapy into the mix. that is working on the second oncological pathway still could reconfirm what the initial therapy would be doing based on the new data that come in, and then hopefully for all patients get to a stage where there is a complete resolution of the tumor in the patient. And we're really convinced that with the smart people that are working in this domain, that we can get to this point where we really can also provide curative treatment for very advanced and metastatic patients. And with that, I want to thank you for your attention. If you want to reach out to us, you can find my details there, but you also have the details of our person in Canada, Hanif, who's also on the line. So don't hesitate to reach out, and I'm happy to take questions from the people in the room. Thank you.
Thank you so much, Wim. Thank you so much for the presentation. The floor is open for questions now. Reza says thank you. Do you mind resharing your screen again, because people might have questions from the slides itself.
Yeah, no worries, no worries.
I'll start it off with the question from the liver cancer
Yes.
slide that you showed.
The last ones, you mean?
It's yeah, this
Okay.
This one. So from Radiomics, from your company, do you sort of build distinctive models for each type of cancer, and then each type of primary metastatic, they're all separate models, and then when you have a client or something with this sort of disease, and you try to use it to predict on the patient directly, so you have multiple different models available that you train just iteratively, and then apply it to patients directly, or do you have one single? Yeah, go ahead.
No, I think there's a lot of aspects to that answer. I think what we first start with is really looking at all the individual tumors, and maybe going back to this image here, this one, I think the first thing to build predictive models from our side is really to measure what's happening at an individual lesion level. So we're really focusing our predictive work on the fate of a single lesion, and then aggregating from there to a patient level, which means that we're actually building models for individual therapeutical compounds. Of course, we learn from the models that we have before.
Okay.
We also have seen that if a model is built for a certain prime metastatic site, often it validates without retraining for a second metastatic site or for another primary tumor location. So as long as you stay within scans from the same modality, that's quite important. It's very difficult to just pipe a model from CT to MRI or something like that. But we have, for example, the HPV model that was trained in primary head and neck cancer patients on CT, and we validated in anal cancer patients from CT. So that was just taking the same model and validating it in another prime disease area.
Okay, so it's really precision medicine. And if you can fit this, you have an incoming patient, you can fit this model specifically to the disease of this patient, and you get their new CT scans and see how, and you predict how, for example, the incoming metastatic disease will progress in the near future. Is that sort of?
Yes.
Yeah.
Yes, and actually, we feel that if you want to make a decision on a patient in a clinic, you really first have to understand that therapy. And that's also why we do all this work with pharma and biotech. By helping them understand their therapy, we also start to understand their therapy better, which means that we can really build models that contain much more of the understanding of the therapy, which is important.
Definitely. And I guess, so this one is built upon CTs, and then, so do you have multiple other modalities as well that you deal with, and how do you, I guess you do collaborate with hospitals to get more training data to get them going, or what other modalities do you deal with?
So we train on CT, we work on MRI, we work on PET, we work on mammography, we work on bone scintigraphy. So yeah, actually we work on on all the kind of imaging that is used in clinical drug development.
Mhm.
And it depends on what kind of disease they're looking at, which is the main source of imaging.
I see our mentor has turned on his camera. Do you have a question?
Yeah, true. Like, I had a quick question, like, to Wim. Like, yeah, the presentation was really great, and I think you guys are doing a really great job, and it looks complex as well. But I wanted to know, like, in one of the slides, you mentioned like, based on the size of a lesion or how it is looking, you're prescribing them an optimal solution, like, and you tell them if this is possible or not. Like, exactly, don't remember the names of those. Like, you take one and others are crossed. Like, so I just wanted to understand, how do you come up with it? Like, what data is being taken, used to make that
You
decision?
know, when you look at a lesion and you want to predict their underlying biology, you mean?
Yeah,
Or
true.
yeah, okay. So there, what you use is input data. Of course, you need to train. So you
Yeah,
need to
true.
have an imaging data set that contains, well, lesions of the kind that you want to predict the underlying biology. But next to that, you also need a ground truth. So when you train, it's not that you first need a training data set that has information of the image and information on the biology. And then you can train your model. And then afterwards, you can run this model on new unseen patients.
Okay, okay. I understand.
Thank you very much for your question. We got a lot of thank yous in the chat here. So feel free to raise your hand if you have more questions. You can also just unmute if you have more questions too. I guess I'll have another question circling back to the ending discussion that you and Leonard had at the end. What do you think is the how do we put patients in the loop of this entire discussion and this predictive modeling processes? Is that being done in radiomics, or is this something that we'll for future explore as well?
Well, I think there's a lot of aspects to this, because on one hand, you can directly put patients into the discussion. And we have quite a bit of grants running where patient organizations are also in, where we listen to what the patient wants and needs. I think another way to bring the patient in is to also identify that the patient is the key element of what you do, whether you're in clinical drug development or when you're in the clinic itself. In the end, it all goes around the patient. And I think in solid tumors, there's a lot of targeted therapies that go down to the level of the patient. But we believe that the level of the patient is not enough. The patient is a collection of tumors in the more advanced disease stages. So you also have to acknowledge that. And it's something that I think when I'm speaking to patients in the projects that we're in, a lot of the more advanced stage patients would like that the community thinks about them as curable entities and not as, let's manage them and let's maybe extend their life a bit. They really want to have a similar approach than the approach we give to like the more early stage patients, where we believe that we can cure them. Because I'm 100% convinced that even for those late stage patients, there is hope. Maybe not today, but in a couple of years. And if we start with the premise that there is no hope, I'm afraid we will not reach the end goal. So within the company, we want to start from the point of view there is hope for those patients. So that's also something that within the company lives quite strongly. And when we have patients like this, you might say it's a very complex case. Let's only look at a selected number of lesions, but we do the effort to look at all the lesions because we feel that the patient deserves that respect. That even when you're an end-stage patient and you contribute in a clinical trial, that your data should be used to the max.
Absolutely. And I guess, has there been, do you guys do early detection work as well? Has there been some work on, okay.
No. So the company really focuses on anything which is treatment related. So it's not no early detection work. There's other people working on that. I think the focus is also quite important. So it's really measurement of what a therapy is doing, understanding what's the phenotype of a tumor that responds more or less to that therapy, linked to the underlying biology that is relevant to that specific therapy. So it's all therapy driven. And yeah, there's other people working on early detection and prevention.
Sure. And I find it to be really interesting that when you collaborated with your I forgot the name, but with your partner, and you learn more about the therapy itself as well. I guess you're collaborating, with the traditional hospital, and is more will be
our collaborations are mainly with companies developing new therapies.
Okay.
So, big pharma, but also small biotechs that have very promising drugs. And for me, this case on screen, it's an interesting one because it's a Swiss biotech. They're working on a PI3K delta inhibitor, which shows some nice potential in uveal melanoma. But if you look at a patient like this, from a clinical point of view, you might say, well, this drug is not working because my patient will not survive. But then again, for this patient, 60% of the lesions are responding. So the question would be, what do we do with the other 40% to get this patient better? And I think it would be a pity for patient that 2 great drugs that work on half of the lesions are stopped in their development, because if you would combine them, they would cure every patient. It's these kind of things that I think are important. Really look at the details, try to understand why something is working or not working, and then find the optimal strategy to cure a patient.
I guess it's interesting because do you realize this as the patient is being treated along the way, or this is not something that you realize before you apply the model or anything, right? So so you realize you see these changes, you see how the patients react to the drugs as you go along, and then do you adjust the model, or do you do you have to do interesting changes along the way, or?
So and this is the way drugs are developed. First, you look at what it does, and then you start understanding what it does and how it does something. So I think to be very efficient at predicting outcome in a clinical setting, you first need to know very much how you link a drug to a patient, or how you link a patient population to a drug. And once you know that, you can look for an individual patient, what's the drugs that should be linked to me to cure me. So indeed, at the moment, it's mainly measurement. It's mainly gaining understanding. It's doing a bit of predictive modeling, but your predictive modeling will be irrelevant if you don't understand the options that it should model.
Wow, this is amazing insight. I have to, if you don't mind sharing this slides with me, I'll share it with our participants.
Yeah, no worries. No worries.
And I see that you referenced a couple of papers here. I'll go and look at it myself as well. So, our participants, I think this might be the end of our Q&A period today. I just want to thank you so much again for your time. It's probably dinner time in Netherlands. So have a good dinner and good evening. Thank you so much for joining us again. If you ever come back to Canada, definitely say hi. We'll say hi again.
Yeah, I will drop by.
For sure. Awesome. Well, thank you so much, everyone else, for joining today. Tomorrow we'll have our last workshop with Laya on deep learning model generalizability and best practices. So we'll see you then. Thank you so much.
Thank you.
Bye, Wim.
Bye-bye.
And everyone else. Thank you.
Thank you, everyone.